Binomial distribution. We are discussing discrete random variable. In statistics, we have so many kinds of random variables. It's already given. Yeah, we knew almost everything. So, chapter 5, discrete random variable. We are going to have two kinds of the common discrete random variables. The first one is the binomial distribution, the binomial probability model. So let me introduce you what is the binomial. For example, we are going to select a person. So please look at this example. Let me make it bigger. It has only two outcomes: alive until 65 and die. Only two outcomes. It's like as the toss of coin. Toss a coin, only two outcomes: head or tail. Now in this example, alive or die before 65. You wanna die before 65? I don't want. I wanna be alive is more than 65, yeah. It's not much, but not 65, yeah. We are going to select three person. Three. So here's the first one, second one, and the third one. Like as the toss a coin 3 times. So we can, so why not? Yeah, we can make the tree. You know, S is the success. What is a success? Be alive until 65. F is a failure. Die before 65. So when I select the first person, it might be alive at 65 or die. And then the second person, it's the same thing, yes or no. The third one, success or failures. So it's like as we toss we toss a coin 3 times. We selected 3 person, success, failures for the first one. The other one, second one, success, failures. So we can make this kind of tree 8 combinations finally. Success. They are all alive at 65. Yeah, unfortunately, the last person died before 65. Success, failure, success. Success, failure, success. Fail and fail, right? So we can make 8 combinations. Let me add probabilities because it is a probability tree. How do you think? How much is the probability here? The first person will be alive at 65. What is the chance? 80%. It was given 80%. So it will be 0.8. You know, it didn't say they are independent, but simply I can assume they are independent. If I will be die before 65, anybody who wanna follow me? You don't have to, because the lifetime, they are all independent. It does not depend on anybody, right? So I plug there's a 0.5 here, is a 0.5 there again, and here is a 0.5 and not 0.5, 0.8. It's all successes. Be alive at 65 with a chance 80%, 0.8. How about the other one, failures? We have to make 100%. So the other one must be 0.2 for failures. 0.2, 0.2, 0.2, 0.2, 0.2, 0.2, and 0.2. Before we made the probability tree diagram, we applied the general multiplication rule. Because the second event depends on the first one. But now, simply we assumed independence. So now we can apply the special multiplication rule to take the last column. So it will be 0.8 times 0.8 times 0.8. The second one, I mean this one, and go down that one. So it will be 0.8, 0.8, 0.2. 0.8, 0.2, 0.8, 0.8, 0.2, 0.2, now 0.2, 0.8, 0.8, 0.2, 0.8, 0.2. So we just go through the path, just follow the path, success, failure, as 0.2, 0.2, 0.8, and the very last one will be 0.2 times 0.2 times 0.2. Good? How much will be 0.8 times 0.8 times 0.8, please?
0.512.
0.5, 1 and 2. Here is a 0.8 times 0.8 times 0.2. And the third one, 2.8 and 1.2. Here's one more. 0.2 times 0.8, 0.8. So how much will be each one? 0.8 times 0.8 times 0.2. How much will be?
0.128.
128. Same as 0.128. 0.128. Next. 1.8, 2.2s. 1.8, 2.2s. How much was it each?
0.032.
0.032. 0.032. And the last one. 0.008. How much do you expect the sum? Why not? 1. Yes, you can try. Sum up, it must be 100% again. So we can make the probability tree diagram. From the experiment, we selected 3 persons and checked they will be alive at 65, success or failures, independently. Now, let me make the random variable. Now the random variable is, okay, let me make bigger. The number of, in chapter 5, we have a discrete random variable. Most of the time, the discrete random variable can be defined as the number of something. So now x, the random variable x is number of successes out of 3. So Now here, x equals 0. What does it mean, x equals 0? No successes. No success. I'm sorry, all died before 65. What is the outcomes then? This one. Fail, fail, and fail. Next. X equals 1. Only one success. Only one success. Only one. Only one. We had 3 outcomes. S, F, 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 S, F, 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 S. Only one success. Now, x equals 2. What does it mean? X was the number of successes. Now, x is equal to 2. 2 successes. Then how many failures? 1 failure. 2 success, 1 failure. 2 success, 1 failure. 2 success, and 1 failure. How many outcomes? 3 outcomes again. But they are S, S, F, S, F, S, F, S, and S. And the last one, x equals 3, all 3 successes, no failure. The very first one, only one outcome, S, S, and S. Good? How much will be the probability? X equals 0. No success, all failures. How much was the probability? 0.008. So the probability will be 0.008. The next one, x equals 1. 1 success, 2 failures. Each had 0.032. How many outcomes? 3 outcomes. So we have to take 3 times 0.032. It will be 0.096. How about the next? X equals 2. 2 successes, 1 failures. This one, and this one. How many? 3 outcomes. Each had 0.128. Then how much will be? 0.3. I don't know, please. 84. And the last one. 3 successes, no failures. We had only 1 outcome. It has the probability 0.512. So here is a 0.008, x equals 0. 0.096, x equals 1. 0.384, x equals 2. 0.512, x equals 3. When I take the sum up, how much do you expect? Always 100% again.